So if you may remember, last session we talked about the transfer function and how to calculate this. The transfer functions and Bode diagrams are really easy to calculate when we are using MATLAB programming language. So the thing with transfer function is if we want to work, if we do have a transfer function in frequency domain, we're going to have something like 1 divided by s plus 1. And then we can use the functions that are already predefined in MATLAB named Bode. But if we have some array, some vector of the data that we exported from some sort of system or a sensor or something, and we want to export the Bode diagram, we may not use this Bode function, which is already predefined in MATLAB, but also we just have to calculate it ourselves. We have to bring it into the frequency domain. And how we can do it in frequency domain, the answer is not Laplace transform, and it is FFT. We should bring it to the frequency domain so we can calculate the spectrum and the frequency components that are included in our numerical data. And after that we brought everything into the frequency domain, we can actually calculate the Bode diagram. So first the magnitude and then the phase. So today we are going to work on this one and see how we can calculate the magnitude and the phase of an array of data that we exported from the sensor or system. So we are using MATLAB again. So if you may remember, we had a command window here, but we are not going to work with this command window. We are going to type edit. So we go to editor window of MATLAB so we can directly start to code. So CLC, clear, and close all. For those of you who weren't here last session, we said that we start every code of ours with these 3 lines. CLC clears every command and information which are on the command window. Clear will clear the workspace or the variables that we defined, and close all will close every diagram and shapes and pictures and everything that we opened from the last code. So CLC clear and close all. Let me save this as the name of manual Bode diagram. So in order to calculate and have an example for manual calculation of Bode diagram, I already exported some data here named sensor data.mat. As you can see, I saved it in my directory that I'm going to use. And so how we can load it is load sensor data. As you can see, is autofilling. So the first step is importing the data that we want to work on. So if I hit run, you see that 4 variables were already saved and defined in our file sensor data.mat. And as you can see, we have an array of input, an array of output, and the sampling time and the sampling frequency. So the first thing I want to do is exporting the length of the input. So I'm going to just write length and then parentheses and then toss this sensor that input.
Sorry.
Yeah,
please. You haven't the screen yet, so we don't see anything.
Oh, I am terribly sorry. Yeah, sorry, my bad. Thank you for saying it. So as I was explaining, sorry if I didn't share my screen. So as you can see here, we have 2 methods of calculation of Bode diagrams. First of all, is the first method is if we do have our data and some sort of transfer function which is already predefined, we can use the Bode command of MATLAB. But if we have some array of data, we may not use this Bode, and we just have to first bring it to the frequency domain using FFT, and then we can calculate magnitude and phase manually, which we are going to do today. So as I was saying, we start our code with CLC clear and close all, and then CLC clears the command window, clears the whole workspace or the variables that we defined, and closes all the diagrams and so on. After that, I exported some data here which we can work on. So we write this command load sensor data.mat, and then we export these 3. So sensor input, sensor output, the sampling frequency, and the sampling time and the sampling frequency. And after that, I'm going to do some calculations. First of all, exporting the length of the sensor input or output, it doesn't make any difference. And after that, I'm going to define U is FFT of sensor input, and I'm going to divide it by L. And after that, I have Y, which is my output. So I can actually directly take it right here and write sensor output. And now I'll calculate it, both of my signals that I had. So first the input signal and second the output signal. The difference between these two variables and these two variables is actually that these first two are in time domain and the other ones are in frequency domain. And as you can see, they are not any real variables anymore, but also they are complex variables. So after that, I just have to calculate the transfer function by myself. So and that would be U times Y, and after that divided by U in power of 2. As I told you before in last session, if we want to use the operations in dyadic method, we just have to add a dot before the star or the multiplication. So and after that, I'm going to define the magnitude. Is mag already? No, it isn't reserved by, let's say, mag n is 20 times logarithm in 10 of absolute value of this h. First, the important part is that you understand what we are doing. We use logarithm of 10 because we want to calculate everything in decibels. So we are first calculating the logarithm of the absolute value and then multiply it by 20. So we have magnitude in decibels. And after that, we can do some adjustments, and that would be bringing the whole magnitude to 0 point. In other words, we can deduct the DC value or the magnitude at a zero frequency, and that would be performed like this: magnitude is equal magnitude minus the initial value. So it's going to be magnitude the first. Let's hit the run and see if everything's right. So yes, we calculated our magnitude and we adjusted it and brought it to the point, and we shifted it actually in a way that the first magnitude is actually 1, and we don't have any magnification at a frequency of 0. So after that, we are going to do the same with phase. With phase, what we want to do is actually using the command angle and then toss this h inside of it. But the thing is, this phase is going to be in radian. So what we want to do is bringing it to degrees. So there is a function in MATLAB. It's called rate to dig, I think. Let's see. Rate to dig using the help of MATLAB. And it doesn't work. Yeah. Yes, exactly. So what we are going to do is calculating the angle and then tossing it in this function, radian to degree. And after that, we want to actually do the same as we did here, and that will be deducting the initial value. And let's say phase minus 180. After that, we are going to calculate our frequency, and we actually doesn't have any. If we want to plot these two, magnitude and phase, alongside. So imagine the Bode diagram is actually two diagrams. One of them is the magnitude, and the other one is the phase. And this phase and the x-axis is actually going to be the frequency in hertz, right? So, but we don't have any frequencies here, so we have to calculate the frequency vector ourselves, and it'll be like this. So fs, the sampling frequency of our sensor of our system that we predefined, in space from 0 to 1, and in actually +1. So the thing is, why did we actually use the half of sampling frequency? It has something to do with the Nyquist channel theorem, as you may know. And the other thing is, we actually multiplied it by linear space 0 till 1. And the thing is, with FFT, we actually need only the frequencies between 0 and half of the domain. So we have to. That is why we use this formula. And after that, I'm going to open a figure. Actually, we don't need that. So I'm just going to write subplot. And my subplot is going to have 2 rows, 1 column, and I'm going to plot on the first part. So 2 rows, 1 column, and then the first part. So I'm going to write here plot, but the problem with plot is that plot is actually in linear scale. So what I'm going to do is using the semi-log. Instead, the semi-log helps me, so I change the scale of both axes to logarithm scale. So I'm just going to write frequency as I defined before, and then because the first argument of any kind of plot function has to be the one that we are illustrating on an x-axis, and the second one is going to be actually our y-axis. So the first thing is magnitude, and then let's see how it works. I'm hitting on run. What is wrong here? Vectors must be the same length. Okay, so frequency. Oh, yeah, exactly. So the magnitude has to be also taken from the first one to half of it. Why again? Okay, let's define something here called L2 is equal to lore of L divided by 2, and then right here L2, see if it works. No, it doesn't work either. Why is that so? Maybe the frequency as well? Yes, exactly. So as you can see here, we actually, as you can see, we have our magnitude here in y-axis, and then we have our frequency in x-axis. And we have our Bode diagram that we plotted by ourselves, I mean manually, and not using any kind of predefined functions in MATLAB. As you can see, our initial value is set on 0 because we adjusted it. And then here we do have a peak. And then, as you can see here, we have an attenuation of, I think, 40 decibels per decade. Yeah. And what you see here is actually kind of not right because we have some problems in our FFT, and our FFT. So actually, the FFT accepts 2 arguments, and we just used one of them here. So you may research after the session if we can improve our FFT so we don't see this error here. But the main thing is that we did it, and I'm going to add some few details here. So I'm just going to use X label, and what I'm writing here is going to be printed on my X-axis, and that would be the frequency in hertz, and then Y label, and my Y label is going to be magnitude in decibels. And what I'm going to do also is to turn on the grid, so we have a better view. So as you can see here, frequency hertz here as my label of x-axis and magnitude, and then the grid is also on, so we have a better view. So after that, we are going to do the same, but this time with the phase. And then the x-axis is actually the same, but here is going to be phase instead of magnitude, and here is going to be phase in degree. So if I hit run again, exactly. But as you can see, the same error we have here at the end of the phase as well. But the main thing is we managed it to calculate both magnitude and phase here. And the first one, as you can see here up here, is actually subplot 2, 1, 1, the first part, and then subplot 2, 1, 2, the second part. So the grid is also on, and yeah, that will be it about the manual Bode plots. After that, we are going to open a new code and talk about the windowing. So sorry. So the thing with windowing again is that imagine that we have a signal here as a function of t, I mean through the time, and this signal is kind of like this. And the problem is if we decide to cut it from here to here, and then analyze this part, and we want to do the FFT on it. The problem is the first point with the end point, they have a difference. They have a difference here, the initial point and the end point. And that would be seen with FFT as like a delta Dirac. And the reason behind that is that we see a really quick change here. So if this part of the signal is going to repeat itself, is going to begin again from here. And if it begins from here, what we have is actually a delta Dirac here. And this delta Dirac, as you may know, does include every frequency in it. In other words, if we have a delta Dirac here, we have a really, really, really sharp peak here. So actually, that is what's called delta of t, right? So here's magnitude and here's time. So as you can see here at t equals 0, we do have a really sharp peak. And this sharp peak, if we calculate the FFT and bring it to the frequency domain, you will see it all over the frequency. So this delta Dirac actually includes every frequency from 0 to infinity. And that's the reason that that this phenomenon, this truncation here, is going to cost us a leakage all across our FFT. In other words, if I duplicate this, if we bring this whole signal in time domain into the frequency domain using FFT, the thing is we are going to see something like this. So imagine that this part of the signal, which we are calculating its frequency spectrum, does have a peak here and a peak here and a peak here. But the thing is, these peaks are not going to be sharp, and they are going to be like this, have some side mountains. And that is what is called a spectral leakage. And if we want to eliminate this spectral leakage, what we have to do is actually eliminating this part. If we want to eliminate this part, one of the solutions for that, let's duplicate this again, and then delete these. What we can do is actually bringing this point to 0 and then bringing this point to 0, so they don't have any difference anymore. So we don't have this this virtual delta Dirac here. One of the solutions for that is actually using a method which is called the windowing function. And the windowing function is a really simple function like this, which is going to be 0 here, 1 here, and then again 0 here. So if we multiply these two together diadonically, the result is going to be something like this. So the signal will start here, then it goes under, then its shape, and then 0 again. So as you can see here, we managed to eliminate this difference, and hence we don't have any spectral leakage. So we are going to work in MATLAB and see how we can apply and how we can calculate this frequency spectrum of a signal that we exported and we measured with a sensor from a tube. which is actually directly related to the practical exercises that you are going to do next week. So first CLC, clear and close all, and then let's load this tube signal and then click on run. So, but I have to save that before. So I'm going to Windows SIG, save it as Windows SIG. So as you can see here, again, we do have a signal that we measured from the tube, and then we have a sampling frequency of 1 megahertz, and then we have a sampling time of 1 million. So after that, again, we are going to calculate the length of the signal. So we can either use the length function, or I'm going to use size as an alternative, and then xpp tube, and then which part. So as you can see here, this is 200,000 times 1. So what we want is actually the first element. So if I don't write anything here, you can see we receive a matrix or a vector here, which tells us the two sizes, but what we actually want is the first one. So if I write here, so you see that it's going to be a number. So here's our size, here's our length, and then again, L2 is equal to lower L divided by 2, and after that I'm going to calculate x capital 2, which is defined as FFT of xpp tube divided by L, and then amplitude of tube 2 times absolute value of x tube. But what we really want to do is just from the first one till L2 plus 1. We just want to use the half of it. What we yet need to define is also the frequency, as we did in the last code. So we are going to write it like this. So Fs divided by 2 times lean space from 0 to 1. And again, so like that. Let's hit run and see what happens if we receive any errors or something. No, we didn't get any, but the main thing is our frequency is actually defined 1 by 100,000. So I'm going to transpose it so we don't have any problems later. So here's also our frequency. After that, I'm going to calculate my windowing function, as we said here. So if you want to calculate this curve, we don't need to calculate anything by ourselves, but we have a predefined function here in MATLAB, which is called han, and this han takes a length as an input argument, and then calculates such thing for us. So I'm just going to write win is equal to han and toss L inside of it. And after that, let's calculate also xpp tube win as xpp tube, and then dyadic multiplication with this win that we defined. So if I hit run right now, you can see that we have a window here, and then we have xpp tube. If I open this xpp tube, yeah, they are 0. Okay, they were already 0, but let's check the end of it. So exactly, as you can see here, the end of the original xpp tube that our sensor gave us, actually we have some values, exactly the thing here that we explained already. But if we open this xpp tube win that we windowed right now and applied this Hanning window on it, as you can see, the end of the signal is 0. So before that, we had in our xpp tube a really huge difference between the beginning of the signal and end of the signal. So as you can see here, in the order of 10 power of 4. But here, as you can see, we eliminated this difference. So this virtual delta Dirac isn't there anymore, and it won't cause us any spectral leakage, as we will see. So the next thing we want to do is actually what we did here was applying this window function of our signal in frequency domain. But what we really want to do is calculating the amplitude of this second of this edited signal that we applied windowing on it. We want to calculate it again, and then let's say amplitude tube, which is windowed, is 2 times absolute value of not x tube but x tube win. But actually we didn't calculate x tube win yet, so I'm just gonna write here x tube win, x capital tube of win is going to be FFT of this, and after that what I'm going to do is write it down here. So if we hit run again, you will see that we actually first brought our windowed signal to the frequency domain using FFT, and then we calculated the amplitude of it, and now we are going to see how this windowing affects our system, our signal. So I'm just going to open a figure and set a name for it, and then let's say windowing in time domain, and after that, yeah, let's subplot. This time we are going to have 3 rows, 1 column, and the first part would be plot this XPP tube, the original signal, and then I'm going to add a title here and write original signal, and then do the same with the other ones. So the second part is going to be my windowing, and the third part is going to be my XPP tube win, and here is the add window, and this will be my windowed signal. And if you hit run now, you will see the exact same thing that we drew in our presentation. So as you can see here, the first subplot is actually our original signal, the second subplot is our Hanning window, and the third part is actually our signal, our recorded signal, but the Hanning window is applied on it. So as you can see here, the end of the signal and the initial value of the signal are both of them are brought to 0, and this bringing to 0 helps us to eliminate the spectral leakage, as we will see now. So this was talking in time domain. The same thing we want to do is in the frequency domain. So let's open another figure and name it comparison with and without windowing. So let's again semi-log x, and then as the first value I'm going to give the vector I'm going to illustrate on my x-axis, and that will be my frequency. But the thing is, we just need half of it, so it's going to be 1 till L2, and then as the second argument I'm going to give the vector I want to illustrate on my y-axis, and that will be amplitude of tube, the original signal I mean, from the first one till L2, because we need just half of it, and then I want to hold on, so I can plot 2 diagrams on just one coordination system, so we can see them on each other and directly compare them to each other. So the second thing is going to be not amplitude of tube, but also amplitude of tube, the windowed signal. So if I hit the run, I hope it works. Yeah, it does work. So as you can see here, in the second figure, we do have 2. Maybe let's improve it a little bit, and let's say line width has to be 2, and the same thing for here, so we see it better. You know what? Let's actually turn the grid also on, so it makes more sense. Yeah, that's better. So as you can see here, the blue signal is actually the original signal that we did in window, and does have some sort of a spectral leakage here, as you can see. And this spectral leakage of the blue signal, of the blue spectrum that you are seeing, is actually the effect that we talked about before. But as you can see here, the orange one, the second one, which is the frequency spectrum of the second of the windowed signal, is really sharp and doesn't have this mountain sides, as you can see here. So this blue chattering that you are seeing here is because of this virtual delta Dirac that we had. But the Henning window function helps us to eliminate this spectral leakage. And as you can see here, this is just something that we have as analytical and theoretical. And in reality, if you do have a sensor and the data of this sensor is going to be really worse than this. So that's why we need to use windowing. And let's add some other details here. So X label is going to be our frequency in hertz. And then the Y label is going to be the magnitude, no, sorry, the amplitude. And then the title is going to be, actually we don't need any title, or do we? Let's see. Comparison frequency spectrum, and then legend as the first argument. The blue one was the original, and then the second one was the windowed. And let's hit run again. Yeah, exactly. So amplitude, frequency, the first one is the original, and the blue one is the original, and the orange one is the windowed function. So let's say, so as you can see here, before a frequency of 100 and after frequency of 10,000, we don't have any peaks. And let's also change the axis. The axis is going to be x0, so let's say 200. And after that, let's say 3,000. So for x-axis, I'm going to just illustrate between 200 and 3,000. And for the y-axis, I'm going to go with 0 till, I don't know, 15,000. And then hit run again, so we have a better view, a zoomed view. Exactly. So here, you will see how windowing helps us to improve our signal. So these were the items that we wanted to talk about MATLAB. So we are going to finish our session with MATLAB right now, and then talk about some practical things in industry about the sampling frequency. So I suppose every one of you is already familiar with Nyquist-Shannon theorem. Nyquist-Shannon theorem says if we have a signal which has a highest frequency component of, let's say, 1000 hertz, our sampling frequency has to be at least 2 times larger. So if we want to sample a signal which has a highest frequency component of 1000 hertz, we have to have a sampling frequency at least 2000 hertz. I'm not going to explain everything here, so you have to know it as a master's student. But the question has to be asked. So what if we have a signal, we have a mechanical system, and we don't know how high is the highest frequency of which is included in this signal. So let's say, okay, we have an unknown signal. This unknown signal that we have, we want to sample it with sample and hold, but we don't know which kind of frequency it has. So what do we have to do? What kind of sampling frequency do we have to have here? So let's say 2 times larger than some highest frequency. But what is this largest frequency? We don't know it. So how do we adjust this frequency of sample and hold element? And the answer for that is that every system, every mechanical, first of all, 2 points. First of all, every mechanical system does have a highest frequency of, let's say, 100K. Actually, it is very, very rare in mechanical systems that we have a frequency, an eigenfrequency or such thing, a signal which is containing a frequency more than 100 kilohertz. It is really, really rare. So what we are going to do is bringing this signal to lab. In lab, we do have some really high technological sampling equipment, and then we can sample it with the highest frequency possible that our equipment allows us. And after that, we do have an idea, a very first idea, which frequency for our sample and hold element is going to be required. So we have a signal. We don't know how high our sampling frequency has to be. So we sample it with the highest frequency possible that we know. And after that, we understand that this highest frequency, the highest frequency that is included in this signal is like 1000 hertz. And after that, we are going to set this 1000, and then our sampling frequency will be 2000. I just wanted to say that as a point. And then about delta Dirac, we did talk, and then about the nodes. One other important point is that if we want to sample some kind of, if we want to do a model analysis of some kind of beam or other mechanical systems, let's say here's our beam, this is clamped here, then we will input some kind of force here or a delta Dirac force here, and then we attached actually one sensor here, one sensor here, one sensor here, one here, and one here. So we do have 5 sensors here, and we are recording them and bringing them to the computer so we can do a model analysis of this. The very important part is the data that you receive from this signal, and the data, this sensor, and the data that you receive from this sensor, and this sensor, and this sensor, and this sensor are sort of similar. So let's say here is the frequency, and here is the magnitude, and the same thing here, the same thing here, the same thing here, and here. So we do have a sensor here, sensor number 1. We exported all the data here, and then we brought it to the frequency domain using FFT, right? So we do have some sort of peak like this. And the second one is going to have the same frequency spectrum, but with different magnitudes. Sometimes it happens that some frequencies are actually absent in one of these frequency spectrums of one of these sensors. The reason behind that is that this sensor, the position of this sensor for this eigenfrequency is actually the node. So that's why we don't see it here. So we see this third eigenfrequency in all of frequency spectrums of all sensors, but we don't see it here. Why? The reason behind that is that maybe this point, this exact point that our 5th sensor is placed, is actually the node of this eigenfrequency. That's the reason behind that. That was one other point that I wanted to mention before we start with Simulink. So let's start with Simulink, enough with the theoretical. So we save this. I will upload them to Moodle for you. So one of the very nice tools of MATLAB that we can use is Simulink. Simulink is some sort of simulation tool of MATLAB, and does have very similarities with MATLAB itself. But in this case, we won't code anything. We just will use some sort of predefined blocks and connect them to each other, which is called the signals. But very important point is that Simulink and MATLAB are connected to each other. You can run Simulink models from MATLAB code, or you can share actually the workspace, the variables that you defined in your MATLAB code and your Simulink. You can share them with each other. So they are completely connected and using the same directory. So in Simulink, as you can see, we don't code anything, but what we have here is actually some sort of blocks, predefined blocks, And we can also define our own blocks. So as you can see here, we have different kind of blocks, such as constant, gain, integrator, logical operators, input, outputs, products, and so on. And in continuous, we do have derivative, integrator, I don't know, maybe dead zones, transfer function, and so on. So what you can do is actually, instead of coding, if you want to define a transfer function and you don't want to code anything, what you can do is actually bringing some blocks here and then connect them to each other, and then from left to right or from up to down, the whole system will simulate. And that is the beauty of Simulink. So we are going to design a very simple simple mechanical design, mechanical system here, very short, and that would be signal and usage of low pass filters and their function. So what I'm going to do is, if you use this search bar, is going to cost you much time. So the best way to start with Simulink is that you know already what you want to do. Since I know what I want to do, I'm just going to click here once and then start typing. So I'm just going to write sine, and as you can see, I do have a sine wave, so the block is important here. And after that, I'm going to write white noise, and then add a block of white noise here, and then add here, first I have to click, and then yeah, let's say sum. And after that, as you can see here, I can bring my mouse here and then drag and drop here, and then the signal will be connected here. So here I do have a sine frequency. If I double click on it, a window will pop up, and then I can actually set some variables here, like the frequency of the sine wave. I enter 50 hertz here, and then here I'm just going to enter the noise with the power of, let's say, is that enough? Okay, let's see. And then the sampling time, yeah, let's make it more little. So as you can see here, I do have a sine wave here, and then I have a white noise here, and then I have a summation block here. And after that, I'm going to add a scope so I can see what happens. And then let's simulate the whole system for 2 seconds and click on run. Yep. As you can see here, I do have a signal here, which is a sine wave. Actually, 2 seconds is also too much. Let's say for just half a second. So as you can see here, I do have a sine wave here, which a noise is added to it, and this sine wave is kind of sharpy, and it's not that beautiful and ready to use, and it does contain much noise. And before we use this and bring it to our digital signal processor or the computer, what we really want to do is to filter this. And the best way to filter that is using a low pass frequency, a low pass filter. About the low pass filters, if you search low pass filter, you will see that low pass filters, what low pass filter does is attenuating. Attenuation of the signal. So let's say here is the maximum frequency that we want to hold. Let's say here is 50 hertz, right? Because our main signal, our sine signal, was 50 hertz. So what a low pass filter does, here's the magnitude, and here is the frequency. Actually, not the frequency, but the logarithm of the frequency in base 10. So what this low pass filter does is actually holding the magnitude here. So here we have a magnification of 1. So as you can see here, here is 0. So it doesn't alter, it doesn't change. This low pass filter doesn't change our signal. But if the signal is larger than 50 hertz, the attenuation will happen. And that is exactly what we want to do. We want this noise that is here somehow. We want to attenuate this, and we want to delete this from our signal. And then this low-pass filter will help us to achieve this goal. Let's get back here. And no, actually, let's talk more about low-pass filters. How we can actually implement low-pass filters in reality is using resistor, capacitor, and then measure here. So this is going to be our input, and this is going to be our output. So the signal comes over here, and if it does have a high frequency, the highest frequency will be transferred to earth here, and the clean frequency that we wanna save is going to pass throughout. So if you look at the transfer function of this circuit in frequency domain, is going to be 1 RCS plus 1. And this is what is called 1 divided by tau, which is actually our parameter here. So the transfer function is going to be like this. So what we are going to do now is implementing a low-pass filter in our Simulink model using this transfer function. So let's head back to the Simulink and then click here and write transfer function. And then you can see here we do have a transfer function. And then this transfer function has to be set up. So I'm just going to add this value here, and then connect this here, and then connect this here. So as you can see, our scope does have two inputs right now. One of them is going to be the sinusoid signal, our original signal that we have, plus the noise, which are summarized together here and connected to the first input of a scope, and then the same signal but filtered using a low-pass filter, and then to the second input. Let's hit run again. And then double click here. So actually that was not what I wanted to do. So let's say 2 subplots. Exactly. But the shape is not kind of nice. I'm not satisfied with the resolution. So let's change the settings, the solution variables. So solver selection, let's say fixed step, and then the maximum size step, fixed step, yeah. The maximum size step is going to be, let's say 1 divided by 1000. So as you can see here, on the first part, on this first subplot, we do have a signal which is polluted with noise. And then in the second subplot, we do have the signal which is filtered using a low-pass filter. And that's how you can implement a low-pass filter in Simulink. You can work with other commonly used blocks here from the library of Simulink and get familiar with it. But since we don't have much time, I'm just going to close the matter with Simulink here. And let's say low-pass filter and save it for you guys so I can upload it for you afterwards. So the next important thing and last thing that we want to talk about today is actually the use of this low-pass filter for anti-aliasing. So as you may remember, the sampling theorem told us that we have to choose a sampling frequency at least 2 times higher than the largest frequency component, the highest frequency component of our signal, in order to not come to aliasing. So what we want to talk about now is anti-aliasing filter. So the main point about anti-aliasing filter is, imagine that we do have a signal. Actually, let's say we have an excitation, and then it comes to the system, which is our plant, and then we do have a response, and then this response will come to a sensor, and then this sensor will go to sample and hold element, and after that, from sample and hold element, we will give it to the digital signal processor, or DSP. So the main point is, and here is measurement. The main point is we have to be sure that aliasing doesn't happen exactly here. Because if aliasing happens here, we have no option to understand, to realize if aliasing happened. If we sample and hold the element, we have no way to understand if this sampled and holded measurement is aliased, whether aliased or not. So everything that we want to do has to happen here. Everything we want to do has to happen exactly here before we bring everything to the digital form. So what we really want to do is adding an anti-aliasing filter. Before that, anti-aliasing filter. And after the anti-aliasing filter stage, we may now sample and hold and process the whole signal. It is very important and crucial for you if you want to work in industry to understand the matter here. So you have to implement your low pass frequency exactly here. In other words, you cannot implement a digital anti-aliasing filter. All anti-aliasing filters have to be analog or hardware. Because as I told you before, if the signal goes to the digital area, to the digital domain, you have no other option to understand if it's aliased or not. You just have to make sure before you make everything digital, from analog to digital, before sample and hold element, you have to implement an anti-aliasing filter here. And anti-aliasing filter has to be hardware. It cannot be a software or any sort of digital filters inside the processor. So it has to be outside of the processor, outside of the circuit, using some sort of analog circuit. That was the other point I wanted to mention before we close this session. Do you have any questions about programming, about MATLAB, about Simulink, and so on? So that seems not to be the case. I just want to announce something and then close this session. And thank you all for your participation before I close the session. But we are planning to have our consultation hours because from the next week, you are going to begin with coding with MATLAB and doing the practicals, the exercises of the course, which aren't mandatory, as you know, and you don't have to submit any sort of reports or something. It's enough if you participate in the quizzes of the course. But we will have consultation hours, same day, same hour. So Fridays from 17 to 18 or 19. And if you have any problems with the practicals, please do not hesitate to participate in the course and ask your questions. We are going to be there for you to support you and answer your questions about the programming and simulation and coding and so on. So if you see your other friends in the classroom, you can tell them if they have any difficulties with coding or with the practicals and so on. Friday 17, so 5 p.m. I am going to be there for 4 weeks to answer your questions about MATLAB and programming. So thank you again for your participation, and we will close our session right now. Thank you, guys.